This is the beginning of lesson 8.4, and you're first going to do a warm-up where you're going to review factoring with GCF. So you're just pulling out the greatest common factor and writing what's left in parentheses. So you're going to do that page first. Then on the back side, you're going to review graphing from vertex form, labeling the axis of symmetry and the vertex. Finding the axis of symmetry and vertex in standard form. This is lesson 8.3. Going from vertex to standard, understanding that if your A value is negative, you will have a downward parabola, which means you'll have a maximum value here at the vertex. So just identify the maximum height of the ball. Remember, height is our Y value. Right? So you're going to identify the Y value that is the highest, which is at the vertex. And then also from lesson 8.3 is graphing from standard form. Also, when you graph, label the axis of symmetry and the vertex. And you'll be able to check your responses with the answer key soon. So getting into lesson 8.4, we are now looking at how do quadratic functions exist in the real world. Here's just a couple of examples. And as I go through this, you're going to follow along and complete your worksheet with me. Make sure you're focusing, not listening to music, you're listening to me, and you're making sense of what it is that's happening here. So here's the first problem. A company offers rectangular pool sizes with dimensions as shown. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? Well, the first thing we need is a basic quadratic function that's going to represent the area of the pool, including the deck. So we have these dimensions here. This one, this length is 2x, the width is x, and the width of the deck around it, all the way around, is 4 feet. So let's see how we could represent this. Something that we can use to fill in any width of the pool that anyone would want. So we have f of x. Now we know that this 4-foot deck around it is going to add 8 feet, because we have 4 feet here, 4 feet here. It's going to add 8 feet to our length of the pool, because 2x is only the pool. You still need to add the 4 feet on each side for the deck. So one of the factors of this area is going to be 2x plus 8. So that covers the length. The width of the pool also is not including the 4-foot decking on each side. So this one is going to be x plus 8, because this 4 feet will add 4 feet over here, 4 feet over here, and as far as the width, it's going to add 4 feet this way and 4 feet that way. This is how we would find the area of the entire space that would need to be made for this pool with the deck. Now we want to find the area of the pool and the deck now that we know our width of the pool is 15. So at this point, we're just going to actually, let's do something better. Let's FOIL this out first. Let's get it into standard form, because it'll be much faster to plug in our 15 once we're there. So 2x times x is 2x squared plus 16x plus 8x plus 64. This is an x. Combine like terms, and we get 2x squared plus 24x plus 64. So converting it, just go ahead and multiplying it out to get our standard form is going to be much faster now to substitute in the exact width that Carolina wants. So she wants 15 feet for the width. So every time we see an x, because that's the width, we're going to plug that in. Okay, now we just evaluate this, and when we multiply everything out and add, we get 874 feet squared. So Carolina needs 874 feet squared to build a 15-foot wide pool with a deck. Part 2 says, suppose the length of the pool is 3 times the width. How does the function that represents the combined area of the pool and the deck change? Explain. So we don't need to write it and work it out. We just need to explain how it's going to change. Well, if that the 2x is being replaced by the 3, which means that our function would be 3x squared, and then plus 32x plus 64, right? Because this part changes. So the factored form, whoops, we're just replacing this part as well. So that's what would happen if this were different. Okay, that's all it's asking. How does the function change? All right, next one. The equation h of t, so the function of t, equals negative 16t squared plus v, this is vertical motion model. So this is the vertical motion model. The variable h represents the height of an object in feet t seconds after it is launched into the air. The term v to the 0 power, or v to 0, is the object's initial vertical velocity, so initial vertical velocity, and h0 is its initial height. Okay, so initial height, initial vertical velocity, and then how the object goes down. A diver jumps off a high platform at an initial vertical velocity of 16 feet per second. What quadratic function represents the height of the driver after t seconds? So it tells us it's 16 feet per second. So the initial vertical velocity is 16. We're going to replace that right here because this is the initial vertical velocity. So we have, oh, this is h. h of t is negative 16t squared plus 16t, because remember we're replacing this part. Can you see it? Let's see. Just this is our vertical velocity is 16, so we leave the t, and then plus 30, which is the height of the platform, and we can see that right here. This is the height, 30, and that's the initial height, right? So we replace the h0 with 30. Okay, how many feet above the platform will the diver be at the highest point of his dive? So we're looking at this. We're looking at the maximum, right? The highest point. Remember that our formula for finding the h value is right here. So we need to plug in b over opposite of b over 2a. We get negative 16 over negative 32, which gives us 1/2. Okay, this is our x value of, this is our axis of symmetry, right? This is like our x value, our h value in the vertex. Okay. Now we need to use this to find our y value, because our y value is the vertical height. So all we do is we substitute this in, just like we did before when graphing from standard form. Okay, we evaluate this and we get 34 feet. Remember, we're looking at the highest point, how many feet above. And so the highest point is 34 feet. The starting point is 30. So the vertex is 1/2, 34 and 34 feet. X value, y value. Okay, find the diver's maximum height above the water if he dives from a 20-foot platform with an initial velocity of 8. So we're just replacing these values. Instead of 30, it's going to be 20. So it's looking like it'd be right here. And the velocity is now 8 instead of 16. So we can just replace this and then use our same steps to solve. We're going to do opposite of b divided by 2a gives us 1/4. Plug in 1/4. And evaluate that. You can use a calculator, and it ends up being 21 feet. So here's our two options. Okay, so now you're going to hold on to this, use it, reference it, and continue on with the next part of lesson 8.4, which is going to be to do the Desmos called Will It Hit the Hoop? And there is a worksheet to go along with it to record your predictions and whether you are correct based off of your parabolas and things. Have fun.